After we saw in the previous two videos of this series, Quantum Mechanics for Everyone, how the energy of electromagnetic waves and light in all its forms is quantized, we have one step left to take towards the idea of a light particle. One of the most important properties of particles is that they are localized in space. The position of classical particles, for example, can be pinpointed in space at each moment of time. Similar phenomena, but of energy packets, was also demonstrated by the photoelectric effect experiment. Whereas, as we have seen, each electron, which is known as a particle, absorbs one entire quantum of energy, h times f, where h is Planck's constant and f is the frequency of the incident light. This particle property of ordinary classical things comes with an important characteristic, which is that when we collide two bodies together, they will bounce off each other or scatter in accordance with the law of conservation of linear momentum. Conservation of linear momentum is a fundamental law of classical mechanics that expresses the processes of collisions between particles and massive objects. Therefore, in order to confirm the particle nature of electromagnetic waves, this property must be achieved in one way or another. In other words, electromagnetic quanta must be able to transfer momentum, not just energy, to whatever they collide with. In the photoelectric effect, the electron was part of the metal and was confined within it. Therefore, its interaction with the light quantum was limited to the process of energy transfer, and the electron was able to absorb all the quantum energy to be freed from the metal. If we now take some nearly free atoms and use high-energy quanta, such as X-ray quanta, for example, the energy of these rays will be on the order of tens of thousands of electron volts, much greater than the binding energy of an electron in an atom, which is only on the order of electron volts. Therefore, this electron could be considered free in this process due to this large energy difference, and this electron will be able therefore to sense the X-ray quantum coming at it as actually a concentrated amount of energy. This represents a good opportunity to study the collision and momentum exchange between the quantum and the electron. When X-rays were incident on these free atoms, it was found that the light emitted was diffracted from its path, and its wavelength was also greater than that of the incident radiation. These X-ray quanta were interacting with the electrons. Of course, to explain the change in wavelength, we know that the energy of a light quantum is a function of its wavelength, and there is no doubt that there is a loss of energy from the light quantum to the electron. However, why would the X-ray quantum change direction? It seemed just very similar to colliding two billiard balls together. Should we treat the quantum of light like a billiard ball? This was the fundamental question. Therefore, Compton tried to treat the problem as if it were a mechanical collision between two particles. Like all collision problems, both energy conservation and momentum conservation are considered during this process. Compton considered that the electron was initially at rest due to the energy difference mentioned previously, and that its initial energy was only its rest energy. The conservation of energy is then given by the conservation of momentum is given by where P sub e is the momentum of the electron just after the collision, pi is the momentum of the incident quantum, and pi prime is the momentum of the quantum detected. Now, all we have to pay attention to are two things. First, realize that the energy conservation equation and everything that results from it is a scalar equation, while the momentum conservation equation is a vector equation. Secondly, we do not care about the momentum or direction of the scattered electron. In the experiment, what we observe is the direction and wavelength of the X-ray quantum, so we want to eliminate the momentum of the electron from the problem. We start with the energy equation. Because we want a relationship between the scattering angle and the wavelength difference of the X-ray quantum, we will write the equation in the form. The momentum of the electron we want to get rid of is contained within E sub e. It is given by the relativistic total energy equation. So we square the energy equation. and substitute for the energy of the electron. Then we solve the equation for the electron's momentum. All of these energy terms can be written in terms of the wavelength of an X-ray quantum. We finished working with the energy equation and solved it for the electron's momentum. Now we turn to the momentum equation and try to solve it for the same quantity. Note that this equation is a vector one, as we said, and in order to connect it with the energy equation, we must convert it into a scalar one. The rule for doing this is to square it. So we expand the square parentheses, so the equation is completely scalar. It is now possible to get rid of the electron's momentum by substituting the last equation into the energy equation, so the result, after some canceling, is This is the equation obtained by Compton. This equation says only one sentence. This phenomenon of electromagnetic quantum scattered cannot be explained unless we treat it as a collision problem and look at the quantum itself as a particle that has both momentum and energy. This was the decisive step in confirming the particle nature of light, which had long been classically known as waves. The energy of the electromagnetic field and its spectrum is quantized, and these quanta are particles of light, now called photons. The final and important question in this video is, why did the electron not absorb the entire photon as happened in the photoelectric effect? The answer to this question later turned out to be closely related to the behavior of these systems and quantum microscopic particles. In the photoelectric effect, the energy of the electron was binding energy. The binding energy in a quantum system is quantized. The electron's absorption of the photon is to move the electron from one well-defined energy level to another well-defined energy level. It's an all-or-nothing process. Depending on the difference between the energy levels in the system, the photon will be absorbed or not. In the Compton case, the binding energy of the electron is really small compared to the energy of an X-ray photon. Therefore, once the electron is freed from its atom, it becomes a free particle and is no longer bound. Thus, its energy is no longer quantized, and it can exchange any amount of energy from the surroundings. Thanks for watching.